very good. Okay, there. So please close the door. Có lịch thi midterm rồi đúng không ạ? Hình như là buổi sáng thì calculus, buổi chiều thì algebra đó. Ok, câu sinh viên luôn luôn hỏi là thưa thầy thi phần nào giới hạn cái gì, chả giới hạn cái gì cả. Học gì thi đấy mà. Anyway, here is what we studied last week. Yesterday when I made that slide, I realized that last week we studied so very little things. We studied the basis of a vector space. That is something like that. A set of vectors v1 up to vn will be called a basis for the vector space V. If S is a spanning set of V and N is linearly independent. So I repeat, basis, that is a set of vectors inside a vector space satisfying two properties. The first one, it must be a spanning set, and the second one, S must be linearly independent. And then we have the examples. The first one is not example, that is only the convention. The convention. We agree that the basis for the zero vector space is empty set. But the second one, that is something we know from the high school for the R3. Usually we have the basis consisting of I, J, and K with the coordinate like that, or by geometry you can imagine in the space, if you consider the coordinate OX, OY, and OZ, then the unit vector lying on those OZs will be called the standard basis for R3. And we generalize it for any n space Rn. The standard basis for Rn to be E1, E2, En with the coordinate like that. Examples, if you consider the R4, they have 4 vectors in the standard basis like here. And then next two examples, we consider the standard basis for the matrix space and for the polynomial space. For the space of n by n matrix, they have standard basis consisting of E, I, J, with I from 1 to n and J from 1 to n. Where E, I, J, that is n by n matrix with almost every entry at 0, except only one. Only is entry lying on the i's row and j's column to be 1, and all others entry at 0. And examples, if you consider the space of on 2 by 2 matrix, they have a standard basis like that. And for the standard basis for P and X, that is the space of on polynomial with degree less than or equal n. It has a standard basis consisting of 1x, x squared, x cubed up to x to the power n. Or if you consider the P3, it will have the basis 1x, x squared and x cubed here. Then the following is the importance of the basis. That is, if V to be a basis for vector space V, ở dưới nói vẫn to hơn thầy, mặc dù các bạn không có mic. Suppose that V and S to be a basis for vector space V, then any vectors inside V will be written in only one way, as a linear combination of the vector inside the basis. That property is very important because we are going to use that to define what we call the coordinate, and that we will study today. And I can claim that that notion will be a kind of exercise for you, and it is very easy to make mistake. Not very difficult. It is not difficult, but however, it is very easy for you to make mistake because it's just a little complexity in calculation. Then we have some more property about the basis and the linear dependence and linear independence. And suppose that S consists of V1, V2 up to Vn is a basis of vector space V. Then any set containing more than n vector must be linearly dependent. So it means that the number of vectors inside a basis is a maximum number of vectors inside a linearly independent set of V. And the next one, from that property we can imply that if a vector V has one basis with n vectors, then any other basis of V must contain exactly n vectors. Or in other words, we can say all bases of the same vector space always have the same number of elements, the same number of vectors. And that number of vectors will be called the dimension. Here, we define it is the dimension of a vector space V. Or here we have two different notions. The first one, if the vector space V has a basis consisting of a finite number of elements, then V will be called a finite dimensional vector space. Otherwise, if a vector space V cannot have a finite basis, then V will be called infinite dimensional. And the dimension is defined to be that number. That is, if S is a basis for V, then the number of vectors inside S will be called the dimension and denoted by din of V. And once again, we come back to what we studied in previous slide. That is the case of zero vector. That will have a dimension 0 because that is the number of elements inside empty set is known. The dimension of V, if the dimension of V equals n and S is any subset of V, then you have three possibilities. The first one, if S is a generating set, then the number of S must be at least n. It is greater than or equal to n. If S is a linearly independent set, then the number of S is at most n, or we can say it is less than or equal to n. Only in the case S is a basis, then the number of vectors inside S equal n exactly. Another property saying that if we know already the dimension of V equal M, and W is the subspace of V, then the dimension of that subspace cannot be more than N, or it must be less than or equal N. And that is summarized in three properties here, A, B, and C, and I leave it for you to read by yourself. And once again, going back to the examples about the standard basis, we get the dimension of the Rn equal n because it has a standard basis consisting of E1, E2 up to En. And the vector space M sub M by N, that is the space of on M by N matrix, because it has a basis consisting of those matrices, then the dimension of that space equal M by N. And the vector space P and X, it has a basis consisting of those vectors, then the dimension of P and X equal N plus 1. And the last line here, that is the case of vector space Px, that is the space of the polynomial of odd degree, any degree. Then it has a basis like that, 1x squared up to x to any power. And obviously that basis consisting of infinitely many numbers. And because of that, we say the dimension of Px equal infinite, or in other words, Px is an infinite dimensional vector space. And then we begin define the four fundamental subspace. Suppose that we are given a matrix A of psi n by n. With that, we can define the row vectors like that and the columns vector like that. We divide it by rows or by columns. Then we can define the row space. The row space of A, that is the subspace of Rn, spanned by the row vectors of A. And similarly, we can do that with the columns vector. The column space of A is a subspace of Rn, spanned by the columns vector of A, or by formula you get that one. And the third one, that is a null space. The null space of A is a set of on solution of Ax equals 0, or by formula you get NSA equal the set of on x inside I, so that Ax equals 0. And if you remember, Ax equals 0 is exactly the homogeneous system of linear equation. And the last one has named left null space of A is here. And then we define the rank of a matrix. First, I record to you the two matrices A and B will be called row equivalent if one matrix can be obtained from the other by using the eliminatory row operation. And our observation saying that if A and B are row equivalent to each other, then they have the same row space. They have the same row space. And how we need that? Why we need that? That is in order to find a basis for row space of a matrix, we are doing as follows. First, the matrix A must be transformed into row echelon form B. Then the non-zero rows vectors of B will be form a basis for row space of B, and obviously that is a row space of A. So that is the way we apply. And here is an example. If we are given a matrix A and you are required to find a basis for row space of A. You do as follows. First, you apply the Gauss elimination. You transform A into B. Now B here is already in the row echelon form, and it consists of 3 non-zero rows W1, W2, and W3. And those vector W1, W2, W3 will be a basis for row space of A. And we can do it for the column space. Here, the same matrix A, but you are required to find basis for the column space of matrix. The first way you can transpose A. Then column of A becomes the row of A transpose, and we can apply what we studied in the previous slide. But here is another way. You keep A like that, you don't have to do the transpose. And once again, you apply the Gaussian elimination. You transform A into a row echelon form like that. But now you consider the column here. Denote the column of A by C1, C2, C3, C4, and the column of B by B1, B2, B3, B4. We pay attention to the column containing the leading one. The leading one is here, here, and there. So we have the first column, second column, and the last column. They are the columns containing the leading one. So with that, V1, V2, and V4 will be a basis for column space of B. And similarly, it implies that C1, C2, C4 will be a basis for column space of A. And the relation you can find it is here. So that is all what we studied last week, and today we will continue from this point. So, as I have just shown you, last week we studied 4 fundamental subspace of a matrix A, and we already studied the row space and column space. We know how to find a basis for row space, and we know how to find dimension for row space. And today we begin with the null space. The null space is, by definition, is that one. Or I repeat it here. If A is M by N matrix, then if we consider the homogeneous system of linear equation AX equals 0, the set of all solutions of that will make a subspace of Rn, and it has named null space of A. Here, by formula you get that one, and you can verify it. I take this occasion to repeat to you, to verify something to be a subspace. You need only to verify property number 1 and property number 6. Only 2 properties among 10 property in definition of vector space. And it is here. If x1, x2 belongs to NSA, that is AX1 equals 0, AX2 equals 0, then we have that one. That is a property of operation on matrices, and it is 0. And the second line has the same things. So by that we see that the null space of A or the set of all solution of homogeneous system of linear equation Ax equals 0 is a subspace of Rn. And because of that, the null space of A we defined from last week. Sometimes we call it the solution space of the homogeneous system of Ax equals 0. You can use any name, the null space of A or solutions space of Ax equals 0. And here is some examples for you. Examples on the calculation.
Mời ba bạn kê lên tính của tôi đấy ạ. Tìm của tôi cái này ạ. Ba bạn đấy ạ. Cả ba. Lên bảng luôn. Chơi không ạ? Nếu các bạn thích trao đổi với nhau, ra ngoài. Sao bạn? Ba bạn cho tôi hỏi, ba bạn bây giờ sẽ lên bảng làm bài tập này hay là ba bạn sẽ ra ngoài ạ? Tôi hỏi rất nghiêm túc, đề nghị một trong ba bạn đứng lên trả lời tôi ạ. Ra ngoài hay lên bảng? Trả lời đi, đừng làm mất thời giờ của những người khác. Ra ngoài hay lên bảng? Không phải tôi đuổi các bạn đâu ạ. Tôi chỉ hỏi các bạn muốn cái gì thôi ạ. Sao bạn nói to lên thế ạ? Bạn ở giữa này ạ, bạn áo trắng này, bạn vừa nói xong bạn muốn gì ạ? Ok được rồi, trật tự hộ tôi cái ạ. So, now here is the examples. You need to find the null space for the matrix A like that. Then, the null space of A is exactly the solution space of the system Ax equals 0. Now, to find solution space, we need to solve the system of linear equation. Gauss-Jordan elimination, we reduce A into Z1. And from here, now Z1 is very important because now I am going to show you. And that technique, that scheme you need to apply from now to the end of the course. Here, you consider the columns in the red here. That is the columns containing the leading one. Then, you pay attention to the other column. The other column is here. Is that one and that one. And it means that the variable x2 and x4 will be free variable. By free, I mean it can accept any value. So here I give x2 the value s and x4 the value t. Any s and any t. Then from here you get x3 equal minus t. And with that you get from here you get x1 equals minus 2s minus 3t. So that is a solution for the system of linear equation like that. But now from here we write again like that one. X now consisting of x1, x2, x3, x4. x1 equals that, x2 to be s, x3 to be minus t, and x4 is t. That one is, you need to know how to write it. That vector or that column matrix equals s times of that columns plus t times of that columns. Or if you consider that is a v1 and that column is v2, we get x equal s of v1 plus t times of v2. That is v1 and v2 are spanning set of that one, of the null space of A. So that is the way you can find the null space of A. And the next one, you need to find the basis for null space and the dimension of null space. The first observation, I say, the row space and column space always has the same dimension. If A is m by n matrix, we observe that the row space and the column space always have the same dimension. Or by formula you can write it here like that, and then that dimension will become the rank of matrix A. In Vietnamese, hạng của matrix A, hạng của một matrix A bằng số chiều của không gian hàng hoặc là số chiều của không gian cột của matrix đó. Mà không gian hàng và không gian chiều và không gian cột luôn luôn có cùng số chiều. That is what we are talking about now. Or here, the dimension of row space or column space of A will become the rank of A, and we denote it by that, or by formula again. I write it here. And then, because we have a null space, and what is it? We need to give a name for the dimension of null space. The dimension of null space will has name nullity. The nullity of A to be the dimension of null space of A. And that we know already. The rank of AT equals the rank of A, because the row space and the column space of any matrix always has the same dimension. So that is obvious. Now we have to have something about the dimension of solution space, or that is something about the nullity. It says like that. That is some observation. If A is an m by n matrix, and suppose that we know A has a rank A, then the solution space of A is equal to 0, which has a dimension n minus A. N minus A. That is the n, and that is the number of columns here, equals the rank of A plus nullity of A. That is whenever you are given a matrix A, you know the number of columns. Then, if you know the rank, you will know the nullity of A. If you know the nullity of A, you will know the rank of A. Then, here is something you should pay attention, because it will give you some hint. Cái nhận xét này sẽ cho các bạn những gợi ý in doing your exercise. The first one, the rank of A. The rank of A, that is the number of leading variable in the solution of Ax equal to 0. Or it is exactly the number of non-zero rows in row echelon form of A. And the nullity of A, that is the number of free variables in the solution of Ax equal to 0. That is, once again, I repeat to you in Vietnamese. Khi các bạn giải hệ phương trình đến tính thuần nhất Ax bằng 0, thế thì số các cái biến mà chúng ta gọi là leading nó số các cái biến leading nó chính là bằng hạng của A, còn số các cái biến tự do nó chính là cái nullity của A. Đấy là những cái mà chúng ta có thể biết được này. Hình như in Vietnamese, it seems to me that in Vietnamese textbook you don't have the definition of nullity of A, but however you have the notion of rank A. And once again, you can remember that the rank of a matrix A, that is exactly the number of leading variables in solving a system of linear equation like that. Now, if A is M by N matrix, and we know already that A has a rank A, then we have the following. Now we have 4 fundamental subspace, and those subspace will have the following dimension. The row space and the column space, they will have dimension A, because it is exactly the rank of A. And the null space of A and the left null space of A will have corresponding dimension. The first one will has a dimension n minus A, and the left null space will has a dimension m minus A. So for the first two cases, they have the same dimension, but for the second last subspace, be careful because they have different dimension. N and M are different. Here are some examples for you. Suppose that we denoted the column vector of matrix A by A1, A2 up to A5, like that. A to be that, and the column denoted by A1 up to A5. Then you are required to find the rank and the nullity of A. That is the first thing. The second thing is you need to find a subspace, a subset of column here, so that it will be a basis for column space of A. And the last one, try to write the third columns as a linear combination of the first two columns here. So even the exercise is a little too long like that, but however, to solve it, not so difficult. Once again, you need to apply row operation to transform A into row echelon form. Here you can see you apply row operation to transform A into B like that. And if the column of A to be A1, A2, A5, now I denoted the column of B to be B1, B2, B4, B3, B4, and B5. And please look at those columns. Which one containing the leading one? The first column, the second column, and the fourth column. That is columns containing the leading one. Then that will give you the rank of A. The rank of A equals 3 because we have 3 non-zero of B. That is the first one. And because of that, the nullity of A will be n minus rank. That is 5 minus 3 equals 2. And for the leading one, because as I told you, the first column, second column, and the fourth column containing the leading one, so those columns will be a basis for the column space of B. That is the basis for column space of B. It means that A1, A2, and A4 will be a basis for column space of A. So that is the next one. And we put it A1 to be here, A2 and here, and A4 is here. That is a subspace of columns of A. Now, the last one, because B3 equals minus 2B1 plus 3 times of B2, it implies that A3 equals minus 2 times of A1 plus 3 times of A2. That is, we write already that AC to be a linear combination of A1 and A2. So that is a requirement of the exercise. So that is we study row space, column space, and null space or solution space as the same. Solution space of a homogeneous system of linear equation, and you know already how to solve it. To solve it, you need to know what is a leading variable and what is a free variable to solve it. But now we are going to study solution of non-homogeneous system of linear equation. By non-homogeneous system of linear equation, you see the right hand side now is no longer 0, 0, 0. We have some other things. So I claim the reason first, and then I will explain to you what does it mean. Suppose that XP is a particular solution of the non-homogeneous system of linear equation AX equal B. Then any other solution of the system can be always written in the following form. X will be XP plus XH. XP is here, and XH is a solution of the corresponding homogeneous system of equation AX equals 0. So now if you look at the whole thing here, suppose that you are given AX equal B, and correspond to that you have the homogeneous system of AX equal 0. Then we know already how to find the solution for AX equal 0, and we call XH, that is the solution of that. And suppose that XP is a particular solution, then any other solution must be XP plus XH. Or in Vietnamese, we can say as follows. Giả sử các bạn được cho một cái hệ phương trình tuyến tính AX bằng B như thế này, trong đấy B không phải là bằng 0 hết. Tương ứng với nó, chúng ta sẽ có một cái hệ phương trình tuyến tính thuần nhất AX bằng 0. Hệ phương trình tuyến tính thuần nhất chúng ta đã biết cách giải, chúng ta đã biết được nghiệm nó ở dạng tổng quát. Chúng ta chỉ cần tìm một nghiệm riêng hay một nghiệm đặc biệt nào đó mà tôi ký hiệu là XP của cái thằng này. Khi đó mọi nghiệm của cái hệ phương trình này bao giờ cũng phải có dạng là XP cộng với XH, trong đấy XH là nghiệm tổng quát của cái hệ phương trình này. Chỉ có thế thôi. And it is explaining here, and you can read it in the slide. And here is the examples for the previous slide. Suppose that you are given a system of linear equation like that, and you need to find the set of all solutions. I repeat that, given a system of linear equation, to solve it, it means that you need to find all solutions. Now what do you do now? First, you write it by this way, and you apply the Gauss-Jordan animation, you get that one. And again, that columns will correspond to the free variable. By free variable, I mean you can give it any value S and T. And because of that, you will get the solution like that one. Here, x3 will be S and x4 will be T. And because of that, you will get that one. S, x3 equal S and x4 equal T. And you can solve x1, x2 according to S and T, and you get that one. And now you see that equals S tie of that one plus T tie of that vector plus Z1. And Z1 will be the particular Z1 will be called the particular system, particular solution of the non-homogeneous system of linear equation. Khi phân tích ra như thế này thì cái chỗ thành phần cuối cùng này chính là một cái nghiệm riêng của hệ phương trình không đồng nhất. Còn hai cái ông này chính là nghiệm tổng quát của hệ phương trình tuyệt tính thuần nhất. So here I write it again. S time of U1 plus T time of U2 plus XP to be the columns. Here it means XP is a particular solution of AX equal B, and XH equal SU1 plus TU2 is general solution for the homogeneous system of linear equation AX equals 0, like that. Now we need to have some more things. The system of linear equation AX equal B. Suppose that we are given that. The first thing, before solving it, we need to know if the system has solution or not. That is, the system is consistent or inconsistent. Consistent means it has at least one solution. Inconsistent, it means that the system has no solution. So how you can know it? Here is some criteria for you to see. The system of linear equation AX equal B is consistent if and only if B, the column B or the vector B belongs to the column space of the matrix A. If B lying inside the column space of A, and here is some example for you. Suppose that A to be that, and X to be that, and B to be that column. Now, suppose that X to be a solution, then we have an equality here. AX equal B. If we multiply two matrices A and X, we get that one. AX to be that, or you can write it in the column. You will get X1 of the first column plus X2 of second column plus Xn of the last column. Or B equal AX will be X1 time of A1 plus X2 time of A2 plus Xn time of An. It means that B is a linear combination of column vectors of A, or B belongs to the column space of A. So that is some explanation for you. So what you need to remember, that is the system of linear equation will be consistent if and only if B lies inside the column space of A, nothing more. And here, the rank of A in case B lying inside, in case B lies inside the columns of A, then we have the rank of A and the ranks of augmented matrices are the same. So we can say it again. The system AX equal B will be consistent if and only if the rank of coefficient matrix equal the rank of augmented matrix. Hệ phương trình AX bằng B sẽ là hệ có nghiệm khi và chỉ khi ma trận hệ số và ma trận bổ sung có cùng hạng, có hạng bằng nhau. Here are some examples for you. Suppose that you are required to find, to verify if a system of linear equation to be consistent or not. Here, the system to be that one, you need to know if it has a solution or not. Then you need only to verify it here. And here, from here you see, the system has infinitely many solutions. That, or if you consider the augmented matrix, it is here and here. You get that one. So the system is here. B is a, that explain to you that the B is in the column space of A. That is a system of linear equation is consistent. Or you can verify that the rank of A and the rank of A of augmented matrix are the same. That is a 2. Then I would like to summarize something about square matrix that that kind of things we do at least twice. Now I explain it just a little more. Suppose that A is a square matrix, that is a matrix of size n by n. Then we have the following conditions are equivalent to each other. By equivalent, I mean if you have one condition, you can imply the other. The first one, A is invertible. Then you know already the second one must be Ax equal B has unique solution for any for any kind of matrix B or any right hand side B. The next one, the Ax equals 0, I mean the homogeneous system of linear equation which has only trivial solution. The next one will be, now that one is a new one. The rank of A must be n. Must be n. That is a new one. And that is equivalent to the fact that n row vectors of A are linearly independent, or the n column vectors of A are linearly independent. And, oh, sorry, I forget to write one more thing. That is it. Determinant of A is non-zero. So, by that you see, if you require to verify only one of that, you can try to show another thing. If you are required to show that A is invertible, you need to show only the rank of A equal n, and then you can imply. And vice versa. If you are required to prove that the rank of A equal n, you need only to show that n row vectors of A are linearly independent. It's up to you. You can choose which one is easier for you to verify. Now, as I promised you, we are going to study the coordinate. The coordinate, that is something we can imply from the notion of the basis. Here I repeat that suppose that B consists of V1, V2, Vn. Suppose that B to be a basis for vector space V. Then, as I repeat already from the beginning of today, any vector inside X can be written like that. Any vector X inside V can be written like a linear combination of V1, V2, Vn, like that. But not only can be written like that, it can be written by only one way. Chỉ viết được thế này một cách duy nhất. And because of that, the number C1, C2, Cn will become the coordinate of x relative to the basis b. Relative to the basis b. And the name is like that, but once again I repeat to you that is something you know already from high school. If you consider the coordinate plane, when you are given a point on the plane with the coordinate 2, 3, we know where the point is. And the coordinate matrix or the coordinate vector of x relative to b, that is a column matrix in Rn, having the component to be the coordinate of x. So that is just only the other name. We can call it coordinate, we can call it coordinate matrix, we can call it coordinate vector, we can call it coordinate columns, any kind. But you need to remember, or you need to keep the name coordinate. I can, because it seems you want to always to know some, to remember something you study already from high school. So I can draw it for you. If you are given a coordinate plane like that, that is R2. And in the R2, you consider standard basis. Standard basis is here. And call it E1 and E2. E1 is 1, 0, and E2 0, 1. That is here. E1 is here and E2. And if you are given a point P with the coordinate 3, 4, you know how to find it. You have it here. And 4 is somewhere here. So the point must be here. Points must be here, P. And you can see P here. That is that vector. You see P will be C times of E1 plus 4 times of E2. And you cannot write P by the other linear combination. So the coefficients 3 and 4 now has named the coordinate of P. But you should remember for me, that is, we need the name relative to the basis B. And because if you take another basis, you will have another coordinate. And here is the reason why I write it. X to the basis B, that is the coordinate of x relative to the basis B. And it is here. So here is some examples. Suppose that we consider x inside R3 and we consider the standard basis of x, then the coordinate of x will be that one, because it is minus 2 times of the first one plus 1 time of that one and plus 3 times that one. Then the coordinate column will be that thing. But now, if we consider another basis of R3, now You can verify that U1, U2, and U4 here, 3 vector here, will be a basis for R3. It is a basis because it is a spanning set and it is linearly independent. Now you are required to find the coordinate of that point according to B prime. How to find it? Then you need to do as following. You need to find the linear combination like that. X must be equal C1 U1 plus C2 U2 plus C3 U3. Or you get that one. X to be that, U1 to be that one, U2 to be here, and U3 to be here. And you need to find the number C1, C2, and C3. That will give you a system of linear equation like that. And to solve it, you get the following things. Gauss-Jordan elimination will lead to here. It means that we have a solution 5 minus 8 and minus 2. 5 minus 8 and minus 2. And that is a coordinate of x according to the basis B prime to be here. So 1, 2 and minus 1, that is the coordinate of x according to standard basis, but the coordinate of x according to the non-standard basis B prime will be that one, 5 minus 8 minus 2. So the coordinate depends on the basis. If we take another basis, you will have another coordinate. That is what we are going to study after the break. So we have a break now.
Rồi, dịch thì dịch nhé. Bạch Tùng Đào đi học không mà vẫn nhận
Đi đồ nữa, đi thằng kia đứng phải đấy, đi quán đi đâu, đi đây, đi đâu, đi đâu, không bao giờ đi về, ok, ok thôi.
Chúng ta học tiếp ạ. Sẵn sàng chưa ạ? Chưa hiểu thì nhắc luôn ạ. Các bạn cố gắng cả giờ này lẫn giờ bài tập cố gắng tranh thủ lúc mà có mặt thầy cô giáo, cái gì chưa hiểu có phải hỏi. Nên tôi rất cảm thấy rất dễ chịu khi mà giờ nghỉ của một số bạn lên hỏi, vì khi mà hỏi thì không biết nó có mấy điều như này. Đối với cá nhân các bạn sẽ hiểu được thêm bài, các bạn biết được chỗ nào chưa hiểu, biết được thêm. Còn đối với tôi thì tôi sẽ biết được rằng là cái giải thích của mình nó chưa rõ ở chỗ nào, và lần sau tôi cần phải giải thích kỹ hơn như thế nào để là có lợi cho cả hai phía. Cho nên các bạn cứ hỏi hỏi thầy giáo, hỏi cô giáo là quyền lợi của các bạn, đừng bỏ cái đấy phía. Nhất là chúng ta sắp đến midterm đến nơi rồi. Okay, next we continue here. Before the break, we see that the coordinate of a vector inside a vector space. That is a notion very important. But however, it depends on the basis. For example, here the x inside R3. If you consider its coordinate relative to the standard basis, the coordinate will be 1, 2, and -1. But if you consider it relative to the basis non-standard b prime, like that, then it will have the coordinate x to the b prime equal 5, -8, and -2. So the coordinate in different bases are quite different from each other. Then one of your exercise, one of your tasks, that is you need to how to change from this coordinate to another coordinate. That is what we say the problem of change of basis. If you change from this basis to another basis, so how the coordinate will be changed. And here is an example. Suppose that you are given the coordinate of a vector relative to one basis b, and you are required to find the coordinate of the same vector, but now relative to another basis b prime. How to do it? And it is here. Suppose that now I take the examples from once again from high school. We consider a very easy case. That is the case of the coordinate plane V. V will have the basis B, U1, U2, and B prime, U1 prime, U2 prime. Suppose that is very small vector space. It has a dimension 2, and it has two different bases B and B prime. Each basis consists of only two vectors, like that. Now, suppose that now we consider, because B is the basis of V, then U1 prime will have a coordinate inside B. The coordinate of U1 prime inside B to be A and B. The coordinate of the second vector U2 prime inside the basis B will be C and U. That is the assumption. We consider that. So what does it mean? U1 prime has the coordinate A, B relative to B, means that U1 prime equal A times of U1 plus B times of U2. And U2 prime has a coordinate CD relative to B. It means that U2 prime equals C times of U1 plus D times of U2. Now, if V inside V, like that, suppose that V has a coordinate K1, K2 inside relative to the basis B prime. What does it mean? it means that V equals K1 U1 prime plus K2 U2 prime. In the previous slide, we know already is U1 prime to be that, U2 prime to be that one. So, you substitute it here. And once again, now you regroup it, U1 in here and U2 in here. You get that one, V now equals that. And you know, whenever you write V to be that one, it means that one is the coordinate, the first coordinate of V relative to the basis B. And that is the second coordinate of V relative to B. That is, if you consider the basis B, the coordinate of V relative to B will be the first coefficient here and the second coefficient here. Or if you write it in the columns, we get VB, the coordinate of V relative to B, to be that one. And if you look carefully about that, that is exactly, you take the matrix A, B, C, D and multiply by the column K1, K2. And once again, if you take a look at A, B, that is exactly the coordinate of U1 prime relative to B, and the column C, D, that is the coordinate of U2 prime relative to B, and here is the coordinate of V relative to B prime. So that is summary of very easy examples. We are going to generalize it here. Now we are going to define the notion of transition matrix from B prime to B. In Vietnamese, ma trận đổi cơ sở. We are given two different bases, B and B prime. We are going to define a matrix to change from B prime to B and from B to B prime. Suppose that B to be that one and B prime to be that one. And you need to remember that the number of vectors inside B and the number of vectors inside B prime are the same. They are n. Now, if B, that is the coordinate matrix of V relative to B. I mean, we take the columns coordinate relative to B. And B prime is the coordinate matrix of V relative to B prime. Then we have VB and VB prime will be related to each other by that formula. Nếu tọa độ của V trong cơ sở B là như thế này, tọa độ của V trong cơ sở B phẩy là như thế này, thì chúng sẽ liên hệ với nhau bởi công thức này. It is very simple one. But however, any complicated are contained in the matrix B. Tất cả mọi điều phức tạp đều nằm trong cái ma trận P của chúng ta. So what is the P? P is a square matrix have n columns. Cái ma trận P này có n cột. The first column is U1 prime B. The second is U2 prime B. And the last one is UN prime B. Or you can say it P to be that one. And the matrix P will be called the transition matrix from B prime to B. Cái ma trận P ở đây là ma trận vuông cỡ n nhân n, nó bao gồm n cột. Cột thứ nhất là tọa độ của cái vector đầu tiên ở này nhưng trong cái cơ sở B. Cột thứ hai là tọa độ của vector U2 phẩy trong cơ sở B, và cột cuối cùng là tọa độ của UN phải cũng ở trong cơ sở B. Cái ma trận này được gọi là ma trận chuyển cơ sở từ B phải sang B. So that is just a little complicated, so I need to say it in Vietnamese. But however, there is one thing I need to insist to you today and next week again. The transition matrix from B prime to B in here in this course or in English textbook are quite different from the Vietnamese textbook. In Vietnamese textbook, that it has named transition matrix from B to B prime, not from B prime to B. I don't know why. I don't know why they have the difference like that. So if any of you take a look inside the Vietnamese textbook, you should be careful with that. The name, just only the name, the definition are the same, but the name is one. Trong sách tiếng Việt thì cái ma trận này sẽ gọi là ma trận chuyển cơ sở từ B sang B phẩy. Còn trong giáo trình này, trong tất cả các sách tiếng Anh của người Anh, người Mỹ đều gọi cái này là ma trận chuyển từ cơ sở B phẩy sang cơ sở B. Cho nên nếu các bạn có dở sách tiếng Việt ra để đọc tham khảo thì nhớ cảnh giác cái đấy, không có là làm bài tập sai mấy đấy. Okay, next. I give you a remark that the basis B and B prime has the same role. Vai trò như nhau, B and B prime. So because of that, if we can exchange the role of B and B prime, then we get the following. Suppose that B is a transition matrix from a basis B prime to a basis B in Rn. Then the first one, P is invertible. The second one is the transition matrix from B to B prime. Now, not from B prime to B, but from B to B prime. Queen B, P inverse. And B, if B to be like that, B prime to be like that, then you can write the coordinate of V relative to B equal P multiplied by V, the coordinate of V relative to B prime. Or we can say the coordinate of V relative to B prime equals P inverse multiplied by the coordinate of V relative to B. So that line and that line are the same. It says only P is invertible and we can exchange the role of P or the role of B and B prime. Now we say something about the transition matrix from B to B prime. That is how we can find the matrix, the transition matrix from B to B prime. Suppose that you are given B to be that one and B prime to be that one. They are two different bases for the same matrix, and here we consider only for n square I. Then the transition matrix P from B prime to B can be found by the following way. You can use Gauss-Jordan elimination to find it. Here, you put them side by side, B and B prime. Here, you put them side by side. Then you have, by that you get an M by 2N matrix. B means I write it in the columns. And B prime also in the column. So B will be an N by N matrix and B prime also N by N matrix. Now we put them side by side to get N by 2N matrix. Then we are going to do as follows. we apply Gauss-Jordan elimination to transform the first part becomes the identity Rn. Then the second part will become something, and that something is exactly transition matrix from B to B prime, from B prime to B. Okay. And here is an example. Simple that you are given B to be that and B prime to be that. There are two bases for R2. Then what we are going to do now? First, you are required to find transition matrix from B prime to B. And then, if you are given the coordinate of V relative to B prime to be 1, 2, then you are required to find the coordinate of V relative to B. How to do it? Oh, okay. You need also to find the transition matrix from B to B prime. The first one, you need to find the transition matrix from B prime to B and then from B to B prime. And we know already that the first one and the last one, they are inverse of each other. We apply what I explained in the previous slide. We put two bases side by side. The first one is here. Now apply the Gauss-Jordan elimination. You get the first one, the first part here becomes the identity matrix I here. And the second part now becomes a P. And P here is exactly P is transition matrix from B prime to B, from B prime to B. And because of that, the coordinate of V relative to B prime equals that. Then the coordinate of V relative to B will be P multiplied by that one. And P now to be that, so we multiply them together. You get the coordinate of V relative to the basis B equals -1, 0. And the last part of the exercise is following. Oh, here you can verify it, so I leave it for you to check because it is very easy. And the last part of the exercise is here. You can have two ways. The first one, you can take P, the matrix, transition matrix we find in the part A, and then you take the inverse matrix. Or another way, you can do it here, but now you write B prime on the first part and B on the second part. Then again, using Gauss-Jordan elimination, you transform it into that one. Then the second one will be the transition matrix from B prime to B. That is exactly the P inverse, and it is the transition matrix from B to B prime. And you can verify it, and it is very easy matrix multiplication now. And now sometimes you will have some examples of vector space which is not quite familiar to you. And here is one of those examples. Now we consider the space of polynomial, not R2, not R3, not Rn. Now we consider the P3, that is space of all polynomial with degree less than or equal to 3. Then we know already that P, it has standard basis 1x, x squared, x cubed inside here. And if you consider the polynomial like that, it has a coordinate. You can find the coordinate of that is 4, 0, -2, and 3. And you are required to find the coordinate of the same P. But now relative to a new basis, the basis consists of 1 plus x, 1 plus x squared, and 1 plus x cubed. And obviously, the first thing you need to do that is to verify that the new basis, the new set here is a basis. But however, that one is easy. Then how you can do it? You can do as follow. P to be that one. That is the coordinate of P inside the standard basis. This is 4, 0, as I told you, 4, 0, minus 2 and 3. And you can find it here by only calculation, by direct calculation. You get the coordinate of P relative to B prime with B, that one. Because if you multiply them together, you get that thing. But however, if you need to find the transition matrix, you can get the same coordinate like that, and you can try it at home, or you can try it during the tutor class. And the next example saying that, suppose that you are given the coordinate matrix of x relative to the basis, standard basis here. You need to find that, and here is the standard basis, so the coordinate will be 5, 6, 7, 8. So that is the coordinate. That is something about the coordinate of a vector inside a vector space. And as I told you, it depends on the basis. And one of your exercise, one of your tasks, that is you need to know how to change from one basis to another basis. You have two ways. The first one, you can find transition matrices. The second one, that is direct calculation. Direct calculation means you need to solve a system of linear equation. By finding the transition matrix means you can apply Gauss-Jordan elimination to find the transition matrix, and then you need to do the matrix multiplication. Chưa nghỉ đâu mà sao là xếp bài lô ạ? Okay, next week we study the chapter number 5, and for the midterm, học đến đâu thi đến đấy, học không chừa cái gì ạ? So we stop here.